We want to determine the exact value of sine 112.5 degrees using a half-angle identity. And we just did this problem using this half-angle identity for sine, where these two half-angle identities are the more common half-angle identities that you'll see. But notice how these two identities below here can also be used as half-angle identities, but they can also be referred to as power-reducing formulas. So just for a comparison, we're going to do this same problem again, but we'll use this identity instead, which again can be called a half-angle identity or a power-reducing formula. Notice that here we have sine squared A, not just sine A. So the identity is sine squared A equals 1/2 times the quantity 1 minus cosine 2A, which I'm going to write as 1 minus cosine 2A divided by 2. Notice how when we first apply this identity, we will have sine squared, not just sine, of A, which is 112.5 degrees. Notice how we'll have to take the square root of both sides of the equation in order to find sine of 112.5 degrees. On the right side, we'd have 1 minus cosine of 2 times A, which is 2 times 112.5 degrees. And all this is divided by 2. So let's go ahead and simplify here. We have sine squared of 112.5 degrees is equal to the quantity 1 minus cosine of, this would be 225 degrees, all divided by 2. And now let's find the value of cosine 225 degrees. And let's do it using a reference triangle as well as a unit circle. To use a reference triangle, we'd first sketch 225 degrees in standard position. So the initial side would be along the positive x-axis. And then we'd rotate counterclockwise. Half a rotation would be 180 degrees. So we have to rotate 45 degrees more to here. And notice how this tells us that the reference angle is 45 degrees. So if we sketch a reference triangle, we should recognize this as a 45-45-90 reference triangle. So we could label the two legs with a length of 1 and the hypotenuse with a length of square root 2. But because we're in the third quadrant where both x and y coordinates are negative, both legs would be negative. So the cosine of 225 degrees would be equal to the ratio of the adjacent side to the hypotenuse, which is -1 divided by square root 2. Or if we rationalize this by multiplying by the square root of 2 over the square root of 2, the cosine function value would be -square root 2 divided by 2. And we can quickly verify this on the unit circle. Here's the terminal side of 225 degrees, and since x equals cosine theta, notice how cosine 225 degrees is -square root 2 divided by 2. So now we know that sine squared of 112.5 degrees equals 1. Here we'd have minus -square root 2 divided by 2, which becomes plus square root 2 divided by 2, all divided by 2. Now let's go ahead and simplify this. We can clear the fractions from the numerator by multiplying by 2. If we multiply the numerator by 2, we must also multiply the denominator by 2. So let's go ahead and multiply this by 2 over 2. Notice in the numerator when we distribute, we'd have 2 plus, and then square root 2 over 2 times 2 would just be square root 2, and our denominator would be 4. So now we know that sine squared of 112.5 degrees equals 2 plus square root 2 divided by 4. But we're looking for sine 112.5 degrees, not sine squared 112.5 degrees. So here we'll take the square root of both sides of the equation. And when we do this, we are going to have a plus or minus, which we'll put on the right. So now we have sine 112.5 degrees is equal to, here we must determine whether we're going to have a positive or negative sine function value. And we're looking for the sine at 112.5 degrees. Well, remember, sine theta is equal to y divided by r. So if we were to sketch 112.5 degrees in standard position, of course the initial side would be here along the positive x-axis. The terminal side would be somewhere here in the second quadrant. And we know the y coordinates are positive in the first and second quadrants. And again, because we're in the second quadrant where we know y is positive, the sine function value must be positive. So we'll have a positive square root, and because we have a fraction under the square root, we can write this as the square root of 2 plus the square root of 2 divided by the square root of 4, and of course the square root of 4 simplifies to 2. So the simplified sine function value would be the square root of 2 plus the square root of 2, all divided by 2. So if you watch the last video, notice how this exact sine function value is the same sine function value we found when applying this half-angle identity as well, which we see here. So the process was slightly different, but of course the result is the same. I hope you found this helpful.